Great stuff. What we need to do today is finish off surface integrals, calculating flux. And I've got some questions set up. Let's do the overview first. This surface integral is called flux, and it's got some applications in magnets, I've been told today, but I'm sure there's others. And essentially, to calculate it, you use this formula. And it contains a P, Q, and an R, which are the X, Y, and Z components of your vector field F. It contains some partial derivatives, dz by dx and dz by dy in particular. And you get them because the surface will be expressed as z equals a function of x and y. And we have this thing called positive orientation, which basically means that if the thing is in a positive and upwards orientation, then you use this. And if it's negative or downwards, you stick a negative in front. And the region D typically is the projection of the surface onto the XY plane. So you put all those pieces together, and what you get is called flux. So this is question 12. Here is our vector field, and the surface is this weird looking guy, and essentially that's D. So they've told us. And this one is an upwards orientation, so that's good news. So to get its solution, what we need to do is, let's see, what do we need to do? Well, since I know D, well, pretty much everything is ready to go. So it's going to be the integral from x equals 0 to 1, and the integral from y equals 0 to 4. Negative p, okay, so this is p, this is q, and this is r. So it's negative of this guy times the derivative of this guy with respect to x, which is e to the y. Subtract this guy, q, times the derivative of this with respect to y. And then you add r, which is this guy. And essentially this is what a dy dx situation. And well, let's see what we get. We get x equals 0 to x equals 1. And we're going to do all of this with respect to y. Well, that's kind of going to be a bit awkward. So I need to do that. So I've got to get this fella done. What's that, from 0 to 4? We've got this guy to do. We have this guy to do. And lastly, we have this guy to do. This one's just going to be negative 8 squared y between 0 and 4. So what's that going to get me? Negative 32x squared. Okay. This one's going to be x e to the y from 0 to 4. If you plug in 4, what you're going to get? You're going to get x e to the 4. Take away, put in 0, take away x. If you're going to do this one, you're going to get 1/2 y squared z from 0 to 4. That's going to get you 8z. Take away nothing. The awkward one is this top one, isn't it? What technique will I use to find this fella?
Integration by parts.
Yeah. So I would probably split this as all of this I'll call F, and this little guy at the end I'll call him J. To go, depends how you do it. I do the FG version of integration by parts, but some of you do the UDV, and that's fine. So leave this guy alone. Integrate him. Differentiate him with respect to Y. Integrate him. So I have this guy plus that guy. And if you integrate him with respect to Y, you just get that. We'll do it from a 0 to 4 again. If you plug in 4, you get negative 4 x e to the 4 plus x e to the 4. And if you put in 0, you get nothing out of that, but you do get an x out of that. So I have got, oh, those two guys give me negative 3. So negative 3x e cubed, check. Hopefully negative 32x squared, check. Plus an x e to the 4, so 4. An x e to the 4 minus x, and plus an 8. And I just realized something that I didn't do. And it means that this answer is wrong. Can you see what I forgot to do in the last one? We're looking for this integral.
And you didn't use the S value.
Yeah. So this should have been y x e to the y dy. Which, if I had looked at it, wouldn't it have cancelled that one out, and I wouldn't even need it. Say this is a negative and that guy's the positive, they would have cancelled each other out. So this guy and this guy isn't necessary. So our answer ends up just being these two terms. So I don't need you, I need you, I need you, and I don't need, yeah. That doesn't sound right. If I replace this guy with plus xy e to the y, our integral becomes 0 to 1, 0 to 4, and all I'm left with is a negative 8x squared.
If we're looking at
it's not right.
if we're looking at the original flux integral, that
Yes.
middle term, that would be multiplying, right? Like that would be 8x cubed e to the y.
Yes. And the first term and the last term essentially killed each other off. Yes. So that's what we would have got. Right, you can obviously go over this yourself there. If this is correct, which I hope it is, then this one is variable separable as well. So I would stick it as this guy followed by this guy. I'll call that one done. You know, I guarantee that I'll have made other mistakes today, so hang in there. More than usual, probably. When you're doing these questions yourself for homework, the process is correct. You just have to watch my details. Okay, next one. The last three, because I've got what 7, 8, and 9, I think, are the ones I'm planning for. The last three questions are going to involve us having to deal with parts of circles in some way or another. Whenever I see parts of circles, it means I'm probably going to go polar. So think about that when you have a flux question involving polar. Now in this question here, the vector field has nothing particularly, that's what I'm looking for, nothing particularly circular about it. But when you look at the surface, can you see that there's an x squared plus y squared going on? So there's definitely a lot of surface things going on. So I do not screw up the first part. It's going to be negative x, negative y, but not z cubed, but that guy cubed. So I've already turned the z into x's and y's. That way I won't make that mistake that I did the first time. So that's a good start. Now, this surface, which is a cone, but it's being cut like here and then here. Now, if you can imagine a cone that's being cut in two different levels, if you project that down to the XY plane, can you imagine what that would look like? Right? If you looked at it from above, what that surface would look like. So if you imagine a cone and you slice it there and then you slice it there, and then you look at its shadow, can you see that you get a donut? Right. So that donut, right, that's the projection on the XY plane that I'm talking about. That donut is D. Now the information for D is all in here. Z equals 1 and Z equals 4. Right, if I put Z, the surface equation up, and then I say, but Z is 1, I get that. But that in turn basically gives me one of my circles. And then if you plug in 4, you get your other circle. So this fella here is what, a radius of 1 and a radius of 4. Can you see that D is very, very circular? So what that is telling me is that when I do this double integral with the region D, that I should be bearing in mind that I'm probably going to go polar at the end. I'm going to keep everything X's and Y's right now until a little bit later. So this fella is going to be the integral, I'll just call it region D right now, negative P, which is this guy. So two negatives make a plus. And then dz by dx. Right, if you differentiate this fella here with respect to x, the answer's going to go here. That's the kind of thing I should probably do over here. And if I do its derivative with respect to x, are you happy with, that's the answer. X over the square root of x squared plus y squared. Are we good with that? Right, so this guy is x over the square root of x squared plus y squared. Take away q, well, take away a negative makes this plus, and it's going to be y. And if you do the y value, symmetry tells me it's the same thing, essentially. And then I'm going to do plus r, and r, we've already figured out, it's that guy. Oh, and orientated downwards, so stick a minus in the front. So x squared over this guy plus y squared over this guy plus z cubed. Yeah. These two can be added together. This thing I'll just leave alone. And we now have this guy, plus this guy cubed dA. I think at this point, we can start doing polar. I will be able to describe this donut as r going from 1 to r going 4. And theta is the whole circle, so 0 to 2 pi. This guy is r. And would you agree that this guy is just r cubed? And then it's an r dr d theta.
I'm
Yes.
sorry, I think I missed something there. How did we get rid of the denominator?
Oh, from here to here?
Yeah.
Right. What I did is I added these two fractions together to give this fraction. And this is basically like something over the square root of something.
Okay, I see.
And then I just cancelled it out. We good? Yeah. Okay. So what we're going to do here is it's variable separable. So I'll call that 1. And the r goes from 1 to 4. And what's that? An r squared plus an r to the 4 dr. And at this point, I'll just say dot, dot, dot. Now, no guarantees I've done that perfectly. I definitely know I've done the method right, but it looks nice enough, so it's probably close to being right. Are we good with that one now? Thumbs up or no? That's a good thing.
Professor,
So, yes.
would you mind going back one more time on the bounds? So I kind of missed that just a little bit.
Sure.
The bounds for Z.
Right. So we are told in this story that it's a cone, but it's being cut at z equals 1, and then later on at z equals 4, right? So you imagine a cone being cut. And so can you imagine this cone being cut? It would, when you drop it down and you look at the XY plane,
Right.
you see this guy. Now, so
Right.
what I did is I plugged z equals 1 into the equation here.
Okay.
And then squaring both sides, I get that, which tells me it's a circle radius 1, which is the inside circle.
Okay.
And then I plugged 4 in here, squared that, and that tells me it's a circle radius 4. So I know what the shape is. What I've been able to do is find out what the radii are. This is 1, and this is 4.
Okay. Okay.
So that's where those r equals 1 to 4 is going to come from. So if you wanted to describe D, right, this region
Okay.
D, it's 1 to 4, and it's the whole circle, right? It's not like the top half, it's the whole thing. And when it's the whole thing, you get 0 to 2 pi. And that's where the other fella came from.
Okay.
Okay. This is the second last question for today. Yeah, they do some weird phrasing, which sounds like a contradiction, but they say something like, evaluate this flux using positive orientation. And they give you this, and they tell you what the surface is, and that's all fine. And then they mention orientated downwards. It seems to me like this bit at the beginning is irrelevant. But it sounds like a contradiction, because you read that and you see positive orientation, and then at the end it mentions that this surface is being orientated downwards. So you're saying, well, is it plus or is it minus? And the answer is, it's always what they tell you the surface is doing. I think the first part is them just saying something which is redundant. You should be finding this flux using a positive orientation technique. Well, since you do that all the time, it's not really necessary to mention it. But if the thing is orientated downwards, doesn't that just mean you stick a negative in front of your answer? So that's how I'm reading that now. So in pretty much quite a lot of these questions, I'll have this field right after the beginning that says, and calculate it using positive orientation. But that doesn't matter. You have to wait to the end to find out what the surface is doing. If the surface is orientated upwards, you're good to go. If it's orientated downwards, stick a minus in it. It's a little confusing, but that's how you're going to read it. Okay, we are looking here at a flux question. Here's our F. So that's going to be my P, my Q, and my R. I'm going to rewrite F as Y, negative X, and instead of 4Z, I'm going to take this and rearrange it to find out what Z is. And Z is going to be 4 square roots of 4 take away X squared, take away Y squared. Are you comfortable where the 4Z turned into that? Do you want to see how I made this become this? Are we good with that, or do you need to see it? I've got one thumbs up. Okay. I need to know D. Right, visual. Can you imagine a sphere being sliced at Z equals nothing? Isn't Z equals nothing the XY plane?
Yes.
Right? So if you take a sphere and you drop it down to the XY plane, isn't D just that? So D will in fact be the complete circle of radius 2. Are you happy how I interpreted that from this information here? Okay, so D is going to be polar. It's going to be R between 0 and 2, and theta, since it's a whole circle again, from 0 to 2 pi. So I believe I've got all the pieces. Here's P, here's Q, here's R. Don't quite have Z, so I better write it in right now. I think I'll do Z in red. This equation has to be rearranged so that it's Z equals a function of X and Y. And it's going to be the square root of 4 take away X squared, take away Y squared, right? It's that guy again. Now here there's a 4Z, that's why this has got a 4. This doesn't have that, that's why this is this. Are we comfortable about that? Is this guy?
Yeah.
Okay. So do some side work while I'm at it then. I know from the formula that I'm going to have to find these two guys, right? And since Z is that guy, a partial derivative with respect to X is going to get 1/2 all of this guy to the -1/2 times the derivative with respect to X, which is this guy. This and this partially cancel, so you get a negative. And this guy comes downstairs as a 4 take away X squared, take away Y squared. Are you comfortable about that one? If I make a mistake, you can tell me. Does that look good? That look good? And can I just use symmetry for the other one? Okay, I think I've got all the bits and probably some bits I don't need. So the flux, which is this guy, is going to be the double integral. Well, let's keep it general just for a little while longer. Negative P. So negative Y times P, negative Y, good, times this fella. Then it's going to be negative X times this fella. And then it's going to be plus r. And r is, I don't have enough room. R is this fella. Okay, let's see what we can do about this mess. It's going to be xy over the square root of 4 take away x squared minus y squared plus another xy over the same thing plus 4 lots of the square root of 4 minus x squared minus y squared dA. And then I'm just seeing if I can do anything style points. Well, at least I can combine those two. That's something. Got that. Anything I could do? I could do so. I don't know if I want to. I'm just thinking about that. Do you know if I combine these two by making a fraction of that, I may get something out of it. I don't think I will get anything useful.
It would
Someone,
take I guess it would take the root out of the top.
and you still have one in the bottom, but yeah, maybe. Let's try it. If I don't like it, I'll pretend I never did it. I have this guy. Over this guy. Are you happy about me doing 2 lines at once there? Basically, multiply that by the square root over the same square root. The 2 square roots cancel out, the other square roots left. Yeah. Which means I have a single fraction. And I have 2xy plus 16, take away 4x squared, take away 4y squared, dA. Okay, time to go polar. Theta equals 0 to 2 pi. R equals 0 to r equals 2. This guy in the bottom is 4 take away r squared. 2xy, I'll have to figure that out in a minute. But let's focus on this. Do you know 4 minus 4x squared minus 4y squared? Isn't that just minus 4r squared?
Yes.
And the 16 is still 16. What I don't know yet is what 2xy is. So I guess I could do that at the side. It's 2r cos thetas times an r sin theta. Nothing very interesting here. Although I could combine that. I guess it is slightly interesting. I get an r squared sine 2 theta. R dr d theta. That is a massively ugly looking answer. Is it doable? What one was this? 8? Let's find out. Maybe I made a mistake, which is not unusual. Interesting. Somehow, I got a sign wrong. And now I can see it. That guy is a minus. These all disappear. That's it. That guy there, right? One of these is a plus and the other is a minus. So whatever one is, yeah, plus and minus. So all that we really were, so if you pretend that I did this right and I got a plus and a minus, all that happened was we had this fella minus this fella
Hmm.
plus 4 of these guys. And that's a much easier integral to do. And it becomes theta equals 0 to 2 pi, r equals 0 to 2, 4, the square root of 4 take away r squared, r dr d theta. So all that mess there, didn't even need it because the first two terms, one was plus and the other was negative, so they actually cancelled out. Okay, make up some time here. This is variable separable. Oh, let's give that the 4 because I want to. R equals 0 to 2. Right, this guy is going to be easy to do. How will you integrate r square root of 4 minus r squared?
That's a U substitution.
Yeah, and won't it be 4 minus r squared and off you go and like 5 minutes later. So come back to that guy. The only difference, and it makes a difference, is that the first one was positive and the second one was negative, so they cancelled each other out, which does make life 10 times easier than what I had. And this is relatively straightforward. But we only have one more to do. Okay. We got this guy to get. This is our f, so we're good there. That makes f x, y, and this guy to the power of 4 is x squared plus y squared squared. So there's p, there's q, and there's z to the 4. Z is this guy. If you raise this to the power of 4, half combined with 4 gets you nice square. So that's pretty nice looking. We've got this region, this surface, which is a cone, but it's cut with the plane z equals 1. So if you imagine this was the cone and you cut it here, and then you looked at what the projection on the floor would be, wouldn't that be a circle? And can I just say a circle radius 1? Can you tell why that would be a radius of 1? Just plug 1 in here and calculate it. So we are looking at the region D as just being what is inside the circle of radius 1. So our vector field in terms of x and y now, our region D is going to be in polar, but we've set it up. So we put all the pieces together. See if I can finish on a good one. It's a double integral of negative p, that guy, negative q, that guy, plus r dA. And just in case you're not happy about this fella, if you take the equation of the surface and you say that z is 1, then you get that, and that gives me this relationship, which tells me that we have a circle radius 1, which is how I got D. So we are going to have theta equals 0 to 2 pi, r equals 0 to 1, negative x, the derivative of this guy. And the derivative of this guy will be 2x over the square root of x squared plus y squared. Subtract y times the derivative of this with respect to y, which is this guy, plus r, which is this guy. So I've got 0 to 2 pi. I have 0 to 1. Bailey, our other dog right now, is biting his little toy. 2x squared plus 2y squared over the square root of x squared plus y squared plus this guy squared dA. I've kind of done 2 lines at once here. If I cut myself on time. If I multiply these together, you get negative 2x squared. If you multiply these two together, you get negative 2y squared. They both share a common denominator, which is this guy. As I move down the list, this fella can be rewritten like this guy, and this fella is just going to stay put. Two x squared cancel, negative 2 square roots. We're almost there. With that guy. Right, at this point here, I think it's ready to be turned into polar. I've already got the D already in polar. You have these two guys that have kind of been following us all the way down. Negative 2, that guy is R. This guy is R squared squared. R dr d theta. This is variable separable. So I'll do this fella. And then I'll do R equals 0 to R equals 1 of negative 2 R squared plus an R to the 4. This guy is 2 pi. This guy is negative 2/3 R cubed plus 1/5 R to the 5, evaluated at 0 and at 1. Negative 2/3 add a 5th, take away a whole load of nothings. Oh yeah. And negative 2/3 add a 5th. The current is 15, 10, 3, 7, 15. So 2 pi, negative 7/15, negative 14/15 pi. And then you go and you look at the question and you notice this, which just means that our answer is that. Whew. Now, did I get that right? That would be a good day for one owl shooting space. I can't count. Somewhere in that process I screwed up, but nowhere obvious. And that's pretty much what I've been doing today. So again, the process is right. As you go through these guys, hopefully you have seen the line where a plus should have been a minus, or a 2 should have been a 4 or something. As I keep saying, I'm very confident with the process. I know I'm doing that part right. It's the details that are killing me. Wonder what the details are. That's good. That's good.
I think maybe when distributing in the R.
I think I saw it. This guy is just X.
I can't see you.
Oh, let me show you. It won't look pretty, but I can at least show you where the mistake went and happened. When you differentiate the square root fella, you don't get 2x because there's another a half that cancels it out. You just get x, which means that this is what you get.
Can you scoot it down so we can see the whole paper?
Yeah.
Sorry.
This should be x, no? This should be x, this should be y. So you only get one of these. So you get one of these, which means you only get one of these, which means you only get one of these. And that basically just filters all the way through, right? So you can imagine that this really should only be 2, which makes this a third, which makes this a third. And that gets you 3/15, 5/15, that gets you -2. And then off you go and you do your answer. So I think that's where I went wrong. I just basically lost a 2 here. And that is going to be it for today. So say hi, guys. I shall see you all on. I'll see you all on Monday. And that's us.
Hope you feel better and have a better weekend, Professor.
Yeah, I think it'll take a few days. But yeah, I will eventually. Thank you.
Take care.
Thank you.